Hello everyone, so in this example I want to look at comparing some entropy of different materials and different compounds and get a feel for what are the different aspects that we need to do in these kinds of comparisons. Right, so let's just get to it. So for the first comparison, we're told that a sample of pure silicon or a piece of silicon containing a trace of another element such as boron or phosphorus. So our question always is which sample or which species has the option for higher dispersion or higher dispersal, and secondly, of course, you can use the argument of microstates. And that is basically if something contains more elements, different elements or whatnot, that means it contains more kinds of matter, and hence it has more options of dispersion, right? So anything that is a mixture of matter has more options of, let's call it, arrangement. So if you think about a crystal lattice of silicon, how the silicon particles will arrange itself in a crystal lattice will have a certain arrangement. But even if you introduce one atom of boron or one atom of phosphorus in that silicon lattice, that one atom has several different places where it can actually go and fit and make a different unique crystal structure to what if it's pure silicon. If everything is just pure silicon, right, doesn't matter where the silicon are, it's all the same structure. Introducing a new element into that makes it a different structure depending on where the boron is located in the structure. Alright, so giving it more options for arrangement means we have a higher dispersion. So therefore, where the silicon that contains the trace element will have the higher entropy, and therefore also the higher standard entropy. Okay, so that's what we're looking for. So something that is a mixture of matter or mixture of elements will definitely have the higher entropy. All right. So our next example, or next question is whether or not oxygen gas at 0 degrees Celsius or oxygen gas at minus 50 degrees Celsius will have the higher entropy. And of course here we're arguing about molecular motion. And the idea is about energy. So oxygen at 0 degrees Celsius will be able to, let's say, move around more, right? Its molecular motion will be higher, and it will be able to disperse energy more. So in other words, the oxygen at 0 degrees Celsius will have higher dispersal. Therefore higher standard entropy. Let's not call it standard, it should actually just be entropy, higher entropy. The standard entropy is at 298 Kelvin, but okay. Alright, so it should have the higher entropy. Alright, because it has the higher ability to disperse energy and matter. Alright, because of its greater molecular motion at higher temperature. Okay, so that's what we compared there. Okay, if we look at 1 mole of helium gas in a 1 liter container or 1 mole of helium gas in a 2 liter container, both at the same temperature. So in a larger volume, the gas should be able to disperse better. That makes a lot of sense because a gas expands to the volume of the container. So in 2 liter, it is physically, the gas, the matter has actually dispersed more. So in the 2 liters, 2 liter, we have a higher dispersion. Right, especially because we're looking at the same gas in the same temperature. So in the larger volume, we have a higher dispersal possible, and therefore it will have the higher entropy. Cool. Our final question looks at if we have 1 mole of oxygen gas at 1 bar pressure, or 1 mole of oxygen gas at 0.0 bar pressure, both at 298 Kelvin. And here we need to think of, what does a lower pressure mean? And a lower pressure is usually associated with a greater volume again. So because the lower pressure is a greater volume, that means the gas at the lower pressure will have the higher dispersal. Alright, and therefore it will have the higher entropy. And that's what we're looking for. So in other words, the oxygen gas at 0.01 bar pressure will have the higher entropy than the oxygen gas at 1 bar pressure. You can actually physically see it, because at 1 bar pressure it will be a highly condensed, or a much more condensed gas, and it will be a very condensed system, whereas at 0.1001 bar it will be a very spread out system, and you can literally see how the matter and the energy is able to disperse more in a system like that. Alright, so that's physically how your brain should work and see it. If the matter and the energy is able to disperse more, move around more freely, has a larger molecular surface, a larger molecule, whatnot, that means it will have a higher entropy. And that's in general what you're looking for, is anything that has more arrangement options, broader area, occupies a larger volume, can disperse more, able to move more freely. Like a gas is able to move more freely than a liquid, is more able to move more freely than a solid. These things will have higher entropy than things that are able to disperse less, able to disperse energy and matter less. Alright, so that's what we're always looking for when we're doing entropy comparisons. Alright, so thank you for watching, and I'll see you in the next video.